Let's take a moment and talk a little bit more about Experiment 8, in particular, microstructures. In Experiment 8, we did Sharpie samples, much like this one right here. The next step would have been to cut these, make a metallurgical mount, and look at the various microstructures after the different heat treatments that we did, like this. This iron cementite diagram can be used as a guide for heat treating. I'm going to use this as our guide, and here is our experiment. I'll try and put these side by side. I rewrote the actual chart. And on the right-hand side here, we have the various Rockwell A hardnesses based on the various heat treatments that we did. And what we see here are the results of both classes, the Tuesday and the Thursday class. Going on down the list in Rockwell A. Now I'd like to talk about the microstructures. And I'll try and do this simultaneously with the iron cementite diagram. Much like this. In the as-received condition, this was cold-rolled steel, and the microstructure in cold-rolled steel, nothing special happened, would be slightly elongated ferrite and perlite. Recall this was 1018 steel, 1018, or it could have been 1020 steel. The two steels were mixed in the drawer. I don't know which one it was exactly, but it's one of these two. Ferrite and perlite. It wouldn't change much as far as the microstructures go. And the first sample that we did was we heated it up to 900 degrees Celsius. Here it is. So let's say 1020. It's easier to see on the graph. 1020. We heated it to 900 degrees Celsius. The idea here is to form 100% austenite. Once the austenite is fully formed throughout the sample, rule of thumb is 1 inch of thickness, or let it soak for 1 hour for 1 inch of thickness. So this soaked for 30 minutes. Ensure that the core all the way through is at austenite. And then we water quenched it. So heat to 900 degrees Celsius and then water quench. In doing so, the microstructure that would have formed after quenching, if you were to take that sample after quench, would be martensite. This has a special name. After quench, it's called white martensite. It's a very brittle structure, also very hard, and you can see that here in the hardness. It should be the hardest in all of this column, and as you can see, it is the hardest. The second example I did was heat treating the sample to 900 degrees Celsius, letting it soak, form 100% austenite, and I tried to do a demonstration of what's called a slack quench. Then I took the sample out of the furnace, out of there, and then I held it in the air, and I was hoping in order to drop the temperature to this region in here, such that the microstructure in this region would be a combination of ferrite and austenite. Austenite is unstable at room temperature. So once this cooled down into this region, of course that was a guess on my part, there was no real timing done, but I was letting it cool down based on color. And then we quenched it. The ferrite will remain ferrite because it won't transform, but the austenite is unstable at room temperature, and the austenite will do exactly what this austenite did. It will form martensite. So the microstructure, when we look at this in the microscope, will be a combination of ferrite and martensite. Again, this particular martensite has that special name of white martensite to indicate there was no tempering done. It was as quenched martensite. The next one we did was a temper. Actually, this one was 900 degrees Celsius. We brought the sample to 900 degrees Celsius, let it soak, and then we quenched it, formed white martensite, and then we tempered it back. Tempered back at 475 degrees Celsius in here, and then let it cool back down. This is standard harden and temper operation. Harden and temper. I'll write that here. Harden and temper. Many steels, or most steels, will go through this operation, and it gives us the toughest, strongest materials for engineering purposes. What happens here is we'll form white martensite in the quench operation, and then this gets tempered back during the tempering at 475, and it has a special name called tempered martensite. It should have the second highest hardness on our column, the hardest one being the actual martensite itself. And then when we temper it back, we'll give back some toughness and lose some hardness in return. So it should also be the second hardest. And as you can see here in the hardness column, it is just that. Next one we did, well, this is basically annealing. Take our sample, heat it up to 900, form 100% austenite, and then let it air cool all the way back down. So it will follow through these transformation lines. No quenching involved, so this graph right here would be appropriate to use. It would follow down, go through all these critical transformation lines and come back to room temperature. The final structure will be exactly what the structure is in this field right here. And that basically is annealing that we did. And the final microstructure would be ferrite and pearlite. The next one, we took the piece. It was already at ferrite and pearlite in the cold rolled condition, and heated up to below lower critical temperature, below A1. And we heated it to 650 Celsius, say 600 Celsius about here. And then did an air cool and a water quench from this region. Since we didn't cross any of the critical temperature lines, the original microstructure remains the same. It started with ferrite and pearlite, and we're going to finish with ferrite and pearlite. And the same with this one. And the hardnesses, as you can see, okay, are the same for the two of them. And that is because we didn't go and be past any of these critical temperature lines to form austenite and physically change the property of the steel. Only did some stress relieving in effect.